Okay, so now we're going to look at problem 4. So problem 4 says, let L be an arbitrary language, and then prove that the language insert L is regular. Insert 1L is regular. And basically what insert 1L is you take all of the strings in L, and then for each one of those strings, you insert exactly 1 at all possible positions. For example, when L is the empty string, comma, UIUC here, then insert 1L would just be you insert 1 in the only possible position in the empty string, and then insert 1 in each of the possible positions in the UIUC string. So we'd like to prove that this insert 1L is regular. And so recall that if L is a regular string, if L is a regular language, then that implies that there exists an NFA, call it N, such that the language accepted by N is just equal to L. And likewise, if there exists an NFA N such that L is the language accepted by N, then this implies that L is regular. In other words, if a language is accepted by an NFA, then it's regular. And if it's regular, then there exists some NFA that accepts it. So a way we can prove that insert 1L is regular is by constructing an NFA that accepts it. Similarly, we should have seen in class that any DFA is clearly an NFA because it's just a special case without any of the extra non-determinism. And we should have seen an algorithm for transforming an NFA into a DFA. So likewise, L is regular if and only if it's accepted by some DFA. So as a way to bootstrap our NFA of insert 1L, we can just say let M equals all the components of a DFA, be a DFA that accepts L. And again, we can do this because L is regular, and if L is regular, then there exists some DFA that accepts L. And now we'll use this DFA M to bootstrap our construction of an NFA. We'll say M prime, so NFA M prime will be the NFA that accepts insert 1L. So our task now is to just construct Q prime, S prime, A prime, and delta prime. So we know that Q is the set of states of M, the DFA that accepts L. And so the idea for our NFA, Q prime, is that we want to keep track of whether or not we've seen a 1. In other words, we have all the original states of Q, or the language L, but we're also going to keep track of a flag. You can call it before and after, or yes and no. And this is just saying that if we're in a state, say q comma before, then we haven't seen a 1 yet. And if we're in the state q comma after, then we have seen a 1. And so, analogously, our starting state then would just be the starting state of q, or the starting state of the original language L, comma before. And we can, again, similarly define any accepting state as just q comma after, because we want to make sure that we've seen a 1, where q was in the original accepting states. Okay. So then now we just need to construct delta prime. So we have 2 cases. So we're delta prime if we've been to q comma before, and then we see the string A, or the symbol A, and also delta prime of q comma after when we see this symbol A. So if we're in state q comma before, that means we have yet to see a 1 in this string. So again, we'll have 2 cases. So if the first case would be if, here I'll say, if A equals 1. So if we do see a 1, and otherwise if we don't see a 1. So if we do see a 1, then we're going to want to make sure that we send q comma after, because basically we just want to skip over the 1. So we stay in the same base state, and we just change the flag to q after. We also want to add in state delta q comma A and before, because it's possible that the original underlying language L contains the symbol 1. So if we just have some string and it has a certain number of 1s, it may have just been a string in the original language. So we also have to send the original delta applied to q comma A comma before. However, if A does not equal 1 and we're still in the before state, then we'll remain in before after seeing A. So in this case, we just return delta q comma A comma before. And then for q prime, when we're in the state q comma after and we see A, then, well, we've already seen a 1, and that's not going to change when we see A. So, oops. And here we just return delta q comma A comma after. And so there we go. So we've constructed an NFA M prime for sigma q prime, s prime, a prime, delta prime that accepts insert 1L. So M prime, we can think of M prime as non-deterministically choosing a 1, or chooses some 1 in the input string to ignore, and then simulates M on the rest of the input string. Basically, here in the delta prime of q comma before, whenever we see a 1A, it either chooses to ignore the 1 and change the state to q comma after, or it doesn't ignore the 1 and just changes it to delta q comma A before. And this is This non-determinism, simplifies the NFA. And so again, just to kind of a recap, the state q comma before means that the simulation of M, the DFA, is in state q, and M prime has not yet skipped over some 1 in the new language. Likewise, q comma after means that the simulation of M is in state q, and the NFA has skipped over some 1. And yeah, so there we go. And that's the solution to problem 4.